In the realm of three-dimensional geometry, quadric surfaces stand as a fundamental shapes, extending the familiar concept of conic sections into the spatial domain. In this video we will be talking about this topic and we'll be exploring some basic exercises in order to understand a little bit better how this concept works.
Quadratic surface. The equation to identify an elliptical parabola is x squared minus y plus squared equals 0. And this equation is identified by having two quadratic terms and the quadratic term and x squared and s squared. With the same thing but different number, and this thing is negative and this thing is positive. The form is closed curve, and this form and here, and this form and here. The equation to identify an ellipsoid, uh, for example, 4x squared plus 4y squared plus 4s squared. This is number. And it is determined by it is a parameter. The semi-major acts in A and becomes the quadrilateral radius, and this is radius of the ellipsoid. The quadrilateral, the semi-major acts B, and this is B, becomes the distance from the center to each pole.
Hi, my name is Mackenzie and my team and will talk about the topic of quadratic surfaces. My team is made up of Fátima García Antonio, Jared Salvador Gil Dolores, Alfonso André Fernández Arellano, and Mackenzie Daniela González Ernesto. I will talk and explain about paraboloid. One is elliptical, where it is come circled, and hyperbolic. Good. Plane x z equal a paraboloid. Plane y z equal a parabola. Plane x y equal a ellipse. This parabol opened of the axis.
Continue the next figure, and it's the elliptic paraboloid. And you will remember the next question. X quadratic is minus y plus c quadratic is equal to 0. This equation it's for this graphic. Yep. And these problems you have only remember these canonic equations. For example, the past is for the sphere is the x quadratic plus y quadratic plus c quadratic is equal to n quadratic. Okay, it's the same for all exercise. If you transfer, you draw the line to try to connect for this equation to the sphere and the canonic expression. It's the same with the elliptic paraboloid and this equation: x quadratic minus y plus c quadratic equal to 0. And that's all for my part. Yeah, continue to this exercise. You will the sphere and you remember the next equation, and this equation say x quadratic plus y quadratic plus c quadratic is equal to n quadratic. Okay, and if you take the 100x quadratic plus 1000 y to 4 leave to 4 and c and 100 c quadratic is equal to 100. In this case, this number is not adequately to this equation, but you will have 100 x quadratic plus quadratic I don't remember how do you say raíz cuadrada, but you take the quadratic I don't know, I don't remember. And well, if you take the raíz cuadrada to the 1000 y elevate to 4 is plus 100 c quadratic 100 equal to 100. You will have a 100x quadratic plus 100 y quadratic plus 100 c quadratic is equal to 10 quadratic or 100. Yeah. Continue the next expression of the next figure. I erase the first case with the sphere. One second. Yes. The next expression is the paraboloid, elliptic paraboloid. The canonic expression, the canonic expression is to this figure is x quadratic plus or minus y quadratic plus minus quadratic is equal to 0. Okay. Then, for example, you have x quadratic minus y quadratic plus c quadratic is equal to 0. Yep. And you sorry. This equation, it's any to construct this figure is this is the x, this is the y, and this is the c.
So we will close this video by solving the next problem. First, we're gonna rewrite the equation in standard form using the square and identifying the surface. So the rewritten equation will give us quadratic x plus 2 times c quadratic plus 6 times x minus 8 times z plus 1, which will equal 0. Once we have that, we'll be following to the next step, which will be grouping the variables. So the first group, the x terms and c terms, which will give us quadratic x plus 6 times x plus 2 times quadratic c minus 8 times z, and this will go minus 1. Then for step 2, we will be factoring the coefficients and factor out the coefficients of quadratic c from the c terms, which will end up having quadratic x plus 6 times x plus 2 times quadratic c minus 4 times z minus 1. Then for step 3, we will complete the square, which will be divided in two phases. So for quadratic x plus 6 times x, we will end up having quadratic x plus 6 times x minus x plus 3, which will be quadratic, minus 9. And for the next phase, which will be quadratic c minus 4 times c, we will have quadratic c minus 4 times z minus 2, which will be quadratic, minus 4. And then for step 3, just to finalize, we will substitute this into the equation, and that'll give us x plus 3 quadratic minus 9 plus 2. Then this will multiply z minus 2 quadratic minus 4. We will close this multiplication minus 1, and that'll be the end of step 3. Now we will follow with step 4, which will be simplifying and combining the two constants we just deduced. So that'll give us as a result x plus 3 quadratic plus 2 multiplying z minus 2 quadratic minus 9 minus 8 minus 1. And we will have as a result x plus 3 quadratic plus 2 multiplying z minus 2 quadratic minus 16. And then we will divide by 16 to normalize, which will give us x plus 3 quadratic over 16 plus z minus 2 quadratic over 8 minus 1. Now the exercise is already done, so the last steps would be identifying the surface. So the equation represents an elliptic cylinder, which the standard form is a minus b quadratic over a quadratic plus z minus b quadratic over b quadratic minus 1, which we will very obviously notice this is exactly the same structure, so that'll give us the well, the answer it's that giveaway really. So the center will be -3, 2 in the xz plane, and the y coordinate is unrestricted in this case, so we will not be having that. The rulings will be parallel to the y-axis, and the cross sections, which will be the ellipses with semi-axis alpha -4 along x and b, which will be equal to 2 times 2 along z. Now, some key observations we will have to be very observant on. That is the absence of the y-axis in the equation, which will confirm this is effectively a cylindrical surface. Also, completing the square transforms the quadratic equation into a recognizable standard form. Then this is very important to get a consistent answer. Also, this method applies broadly to classify quadratic surfaces like ellipsoids, hyperboloids, and paraboloids. And just to finalize, this exercise illustrates very well how algebraic manipulation reveals geometric properties of 3D surfaces.